So last time we were in lecture, we had a discussion of boundary conditions for mass transfer. And I want to check one thing, make sure that the sound is properly turned on. Okay. And we considered a phase interface as shown here in this diagram, where we have a unit normal pointing from one phase to another. This could be, for example, a liquid in phase 2 and a gas in phase 1, or a solid in phase 2 and a gas in phase 1, or a liquid in phase 1. And we use this nomenclature that's shown on the right to describe the jump boundary conditions, these special brackets, to denote evaluation of the quantity in brackets on one side of the phase interface, that is in phase 1, and subtract whatever that value is from the value on phase 2, in phase 2. We derived an expression that basically tells us that in the absence of adsorption and chemical reaction at a surface, that the amount of material that comes to the phase interface from one phase has to leave in the other phase. In other words, there's no net accumulation of material at the interface in the version of the jump mass balance that we derived last time. In this lecture, we've allowed components to adsorb and also allowed surface reaction to occur. Last time we talked about the extension of the jump mass balance to a situation where we allowed both chemical reaction and accumulation of components to occur at that surface. And we defined gamma sub A as the moles of A adsorbed at the interface per unit area. And again, if there's no material adsorbed and if there's no chemical reaction, the result of this term in brackets, which is simply that the net rate of material that comes to a phase from one side has to leave from the other. That is, that no material can accumulate at the interface if the reaction term and the non-steady state term are zero. We then considered cases in the limit where the interface is stationary, one where there's no chemical reaction and no adsorption, and we showed that this required that the flux of material arriving at the interface in one phase had to be equal to the flux of material leaving the interface in the other phase. Now, these fluxes are dotted into the unit normal at the phase interface because we're only interested in the material that can actually transport through or across the phase interface. This condition was coupled with the condition for chemical equilibrium at the phase interface, and we discussed how to write the chemical potential in terms of activity and ultimately in terms of activity coefficients in order to develop the expression that's shown as equation 11 here. And it is an expression for the partition coefficient for a component at a phase interface. And so it's the ratio of the concentrations of components, component A in phase 1 right at the interface, divided by the composition of component A in phase 2 just at the phase interface. This is defined as a partition coefficient. It is the thermodynamic partition coefficient. We would know this in other fields as the solubility. You can use approaches such as Henry's law and Raoult's law to develop mathematical expressions for this solubility. Now, we use this to make the point that concentration at a phase interface could be discontinuous, and this is somewhat different from heat transfer in the sense that in heat transfer, the temperature is always continuous at a phase interface. That is, you can't have temperature jumps at an interface like this. But with concentration, you can have a jump in concentration at that interface. What is continuous at the interface is the chemical potential of A in either phase. And so we went ahead and talked about a case, which I labeled case 2 here, where we said that phase 2 is impervious to A. For example, it's a solid catalytic surface, and we looked at the mass balance in that case, allowing now for non-steady state behavior and also for chemical reaction. We noted that when the phase interface was at steady state, the amount of material brought to the surface had to be equal to the reaction rate of A on the surface, and we looked at an example of first order kinetics that are shown here. You can use whatever kinetics are appropriate for the circumstance under consideration. We talked about how to relate the concentration of a species adsorbed to a surface to the concentration of that species in the solution or gas phase just next to that catalytic surface. This is often important because it's often possible to measure concentration in the solution or gas phase next to the surface. It's often possible to measure that value easily, and it can be difficult to measure the surface concentration accurately. And so we need a relationship between these two quantities. And we get that through a simple model of adsorption and desorption. This is just one way of looking at this problem. If the physics are different, then of course the modeling will be different. We argued that the rate of adsorption was proportional to the concentration of A in the phase, gas or liquid phase next to the surface, times the amount of open spots or spaces on that catalytic surface, and that the rate of desorption be linearly proportional to the number of molecules that were adsorbed. So this is one picture of the physics of how adsorption and desorption can occur at a phase interface. We then put this model into the expression for the time rate of change of the into the mass balance, essentially in equation 21. We considered a situation first where the system was at steady state and there was no chemical reaction, and this led us to derive the so-called Langmuir isotherm, and to derive it in this case from a kinetic perspective rather than from a thermodynamic perspective. And so the concentration of A adsorbed on the surface then depends on the maximum concentration of A that can be on the surface, this ratio of adsorption to desorption rate constants, and the concentration of A that's in the phase next to the surface. Now, we ended the lecture last time by saying that if there was surface reaction, for example, first order reaction, we can put that result back into equation 21, and if we then apply the model at steady state, we get the expression that's shown here for the amount of A adsorbed at the phase interface, and you can see how the reaction rate constant then modulates the expression relative to the simple Langmuir expression. Now, one of the things to note is that if you have a fixed value of the concentration of A in the phase next to the surface, as you allow the reaction rate constant to go to infinity, that is, as you allow A to be consumed essentially infinitely fast at the surface, then this term, the denominator of this term, gets to be very large, and gamma A goes to 0. And so as the rate of chemical reaction becomes much faster than the rate of adsorption, then the concentration of A on the surface drops to 0. And so we've seen this boundary condition in some earlier problems that we worked where we assumed infinitely fast kinetics, and this drove the concentration of A actually on the surface of the reactive catalytic surface to 0. Now let's look at a third case, and here we want to talk about a situation where the flow in phase 1, for example, the gas or liquid that is next to the catalytic surface, which we're labeling phase 2, we want to talk about a situation where that flow is not quiescent, but where it is being stirred rapidly, or there's fluid flow that brings about a great deal of convective motion in the fluid, and so the mass transfer becomes dominated by that convective motion. Now, I'll show you later how to model this phenomenon in more fundamental detail, but for now we'll just note that in these cases, very typically in chemical engineering, we will write the net rate at which component A comes to that phase interface in terms of a so-called mass transfer coefficient. And that mass transfer coefficient is is simply a proportionality constant that relates the flux to the concentration driving force in the phase next to the catalytic surface, in this case, or next to the phase interface. Ca infinity in phase 1 is the concentration in A in the bulk that is far from the interface, and Ca0 is the concentration of A right at the phase interface. And this is very similar to the way one would write a heat transfer coefficient, where we write the heat flux, the net heat flux, in terms of a heat transfer coefficient H, and the temperature driving force being the temperature far away from the phase interface and the temperature just at the phase interface. So this is entirely analogous to the way we would define a heat transfer coefficient. Now, let's look at a case where the first order adsorption and desorption occurs at the same time as convective transport from phase 1 to the surface. And so at steady state, the net rate of transport of component A to the surface can be written from the bulk phase 1, that is the gas or liquid next to the catalytic surface, can be written in terms of the mass transfer coefficient as we've just defined. However, at steady state, the rate at which you bring component A to the surface has to be equal to the rate at which it is produced or consumed at that surface, and that also has to be equal to the net rate of adsorption and desorption of A at that phase interface. All of these three processes have to be equal to one another at steady state. If you had one of these processes, either the convective transport, the reaction at the surface, or the adsorption and desorption that were a little slower or faster than the other, then one would have accumulation in the system, and the steady state approximation wouldn't apply. And so at steady state, these three processes are equal to one another. Now, you'll note that I've used a simpler model than we used previously for the adsorption and for the adsorption step. I've just said the adsorption is proportional to the concentration of A in phase 1 right at the phase interface. Now, this is a little bit this is simplified relative to the Langmuir description that we used on the previous page, but I'm trying to show you basic principles here, and you can put in any model of adsorption, desorption, any rate kinetics that are appropriate for a given situation. And so we can reorganize these results, particularly the second two relationships, to give the following relationship between the concentration of A adsorbed on the surface and the concentration of A in phase 1 just next to the phase interface. Now, this includes both an equilibrium constant, which is the ratio of the desorption to the adsorption rate constant, and it also includes the chemical kinetic rate, rate of reaction term. And if the rate of chemical reaction is very slow, or essentially is negligible, then this term in the denominator goes to 0. And the concentration of A on the surface becomes proportional to the concentration of A in the phase just next to the surface. And the constant of proportionality is related to these adsorption and desorption rate constants. So this is another way of viewing in a heterogeneous adsorption case. This is another way of viewing essentially the condition of chemical equilibrium. That is, this K prime, this ratio of adsorption and desorption rate constants, if you were to write out an expression for that, you would see that it's the ratio of the concentration of A in the bulk to the surface. And so, again, this ratio is a partition coefficient. And we see that come up out of this model again. Now, if we solve for Ca0 now in terms of Ca infinity using this portion of equation 28. And the reason we want to do that is that it may be difficult to measure Ca right at the phase interface. The measurement of Ca in the bulk of the material is often a straightforward activity. And so we're motivated to try to relate Ca0 to Ca infinity in terms of being able to make measurements that we could then compare with a model of mass transfer in this system. And so if we do that, we can write we can rearrange the expression for Ca for the net flux of material to the interface as shown here, and I can write then the concentration of A at the phase interface in terms of that in the bulk, and the connection is given just by these by the mass transfer coefficient, the chemical rate of reaction, and this ratio of adsorption to desorption. Now, this is can be reorganized into something that's perhaps a little more familiar to you, if we can do the following. If we write the mass flux as the mass transfer coefficient times Ca infinity minus Ca zero, and further define an additional mass transfer K as the overall mass transfer coefficient, then I write the flux of A to the surface just in terms of Ca infinity. And the benefit of this approach is that if I have an expression for K, this overall mass transfer coefficient, then I'm able to determine the flux of A to that surface based only on measuring Ca infinity, the concentration of A in the bulk. And so if we insert this definition of Ca0 into this definition for the overall mass transfer coefficient, we can simplify that expression to the following form. And equation 35 is significant in that it starts to give you, in a mathematical sense, something that you may have seen much earlier in your chemical engineering career, and that is that you have the 1 over this overall mass transfer coefficient depending upon essentially 3 resistances to mass transfer. One is the mass transfer resistance that is at the in getting the component A from the bulk fluid to the phase interface. Another resistance is provided by the rate of chemical reaction at the surface of the phase interface, or at the catalytic surface. And a third resistance to mass transfer is given by the adsorption phenomena, or the rate of adsorption. So the overall rate of mass transfer can be ascribed or can be influenced by the rate of adsorption, rate of reaction at the surface, and rate of convective transport to the surface. And any one of these phenomena could be dominant depending upon the situation of interest. And so what's examined in the rest of this particular set of notes are conditions where limiting conditions, if you will. And so if the reaction rate constant is very slow relative to the rate of adsorption and the rate of convective mass transport, then if you plug this result into the expression on the previous page, you can get that the flux is basically dominated by the chemical kinetics, and in that sense, Ca infinity is simply related to the reaction rate constant and the concentration of A at the surface. And this concentration, gamma A, be determined from the thermodynamic, from the modeling earlier that relates gamma A to Ca infinity. Now, if the mass transfer through phase 1 to the surface is limiting relative to adsorption and the chemical rate, chemical reaction at the surface, then the flux depends essentially only on the mass transfer through the fluid phase to get to that surface. And the third case is, of course, if the adsorption is slow relative to convective mass transport and chemical reaction, then the flux becomes dominated by the adsorption, essentially the rate of adsorption. So you can only move material to the surface as fast as you can adsorb it onto the surface, because the convective transport and the chemical reaction are very fast in this case relative to the rate of adsorption. So that's all we have to say about this section of notes. This gives us a rather complete package of boundary conditions to work with. The next section of notes, which is entitled For Multicomponent Final.pdf, now I want to briefly introduce the concept of a multi-component constitutive relation for mass flux. And so up to this point, we have introduced and solved several problems using a very simple form of Fick's law. And what I want to show you now is how that result is generalized for the case of multi-component transport. And it is possible to derive the result that is shown in equation 1 from irreversible thermodynamics. We will not do that because the time to work through that derivation in detail, in my opinion, doesn't justify the expenditure of that energy. And so I am going to simply present this result to you as the most relevant one for use in multi-component transport, but understand that it's not an ad hoc expression, that there is there's a good thermodynamic basis to use this particular form, and in particular this form of the mass flux is consistent with the laws of thermodynamics, particularly the second law of thermodynamics. And so the expression that is used in this case gives a relationship between the diffusive flux of component A and the gradients that can lead to mass transport. And the gradients that can lead to mass transport include temperature differences. We will see a bit later on that differences in temperature can lead to mass flows in a system, and this is the process of so-called thermal diffusion. And there are thermal diffusion coefficients that are associated with this process. Those are dA superscript T. And so this particular model for the diffusive mass flux accounts for thermal diffusion. The second term that is written here includes the molar concentration and the mass concentration of a mixture of interest. It includes a sum over all of the components of the molecular weight of species A, as well as the molecular weight of all the other components, the binary diffusion coefficients, or excuse me, the multi-component diffusion coefficients DAB, and also the generalized driving force D sub B, which has a subscript, which is underlined. And this generalized driving force essentially is related to the gradient in chemical potential in a mixture, and it recognizes that it is the gradient in chemical potential that drives mass transfer. And if you imagine that this term is related to the gradients in chemical potential, you can write that out further in terms of the dependence of chemical potential on concentration. Omega B here is the concentration of each species in terms of gradients in pressure, and in terms of differences in species-specific body forces. So the first term in equation 2 is basically what we will show to be essentially an expression of Fick's law. So this is concentration gradient driven diffusion. This model reflects the possibility that the mass transport of A can be dependent on concentration gradients in all components, and the sum is taken over all components except A. And so if you think about this in a binary situation, if you have a concentration gradient or a mass fraction gradient in component A, it automatically gives rise to a concentration gradient in component B, simply because there are two components and the mass fractions have to sum to 1. This model allows for hydrostatic pressure to have to cause mass transfer, and we will come to know this as pressure diffusion, and we'll see how this works in real problems. This term is basically the term that drives mass transport when you have a pressure gradient in a system. And so if you think about systems where, like a centrifuge that's used to centrifuge solutions to perhaps separate blood platelets from blood serum, or to separate particles from a liquid. The reason particles and the reason you get separation in a centrifugal field is that centrifugal field introduces a pressure gradient, and that pressure gradient then drives mass transport. V sub A bar here is the partial specific volume of component A, and 1 over rho is the specific volume of the mixture, or 1 over the density of the mixture. The last term here, the species-specific body force, this is how phenomena like electrically driven transport would enter, where if you apply potential across an aqueous solution of sodium chloride, that causes the sodium ions to move in one direction, the chlorides in another, and largely nothing to happen to the water. And so there we talk about species-specific body forces, these F sub A and F sub B terms, which can drive mass transport. This is also where if the body force on molecules in a multi-component mixture is gravity, F sub A is just replaced by G. Gravity acts the same on all constituents, and you can see that this term goes away if gravity or some other uniform body force is acting on the molecules in the system. Now, you can show, as we showed earlier, that the sum of these J sub A's over all of the components in the system is equal to 0. Remember, J sub A is a diffusive flux. It's not the total mass flux in a system, which we would denote by the variable N sub A. The sum of the J sub A's have to be 0, because if you have one component diffusing in one direction in a binary system, that's equivalent to having the second component diffusing in the other direction. So these J sub A's have to add up to 0, and one consequence of that is that these D sub A's have to add up to 0, and so that also keeps the thermodynamic driving force consistent. And so one of the homework problems we'll do is to prove that this sum, which you sum it over D sub A, all the D sub A's is equal to 0. Now, a lot of this basic theory is derived and laid out in a classic book in this field by Hirschfelder, Curtis, and Bird. Now, this is the same Bird that is the co-author of your textbook, Bird, Stewart, and Lightfoot, and it's on the molecular theory of liquids and gases in chapter 7 of that book. And they have shown for a variety of cases of interest that the DAA terms are equal to 0. Now, these are basically terms where these generalized multi-component diffusion coefficients, and we'll show what their form is in a little bit. But one of the relationships between these is that the DAAs are equal to 0. I should note while we're here that this particular result, equation 1, was derived from the kinetic theory of gases, and so that's the foundational underpinnings for our study of multi-component transport. Since the sum of these diffusive fluxes have to be equal to 0, two things have to happen. One is that these thermal diffusion coefficients have to sum to 0, because you can imagine a situation where you have a temperature gradient, but gradients in no other components, and these generalized driving force terms also have to sum to 0, because you can imagine a situation where the temperature is constant and where only, for example, gradients in concentration drive transport. So these two constraints basically reduce the number of multi-component diffusion coefficients that are independent, or introduces relationships between them. And now, show that here in just a moment. Since the sum of these generalized driving forces equals 0, we can extract one of these terms arbitrarily and write all of the others in terms of that one, or if you will, write the generalized driving force for component C in terms of the driving forces for all the other components. And we introduce this back into equation 5. And if we do that, we can write equation 5 in the form that is shown here. And since we can fix at least n minus 1 of these driving forces arbitrarily, then each of these terms in brackets must be 0. This is a sum, if you will, if you write it out over several components. And that means that the terms in brackets here have to be 0, and this provides further relationships between the multi-component diffusion coefficients, these DAB and DAC coefficients. And so, for example, if we have a binary system, that is, where n in all of these sums is just equal to 2, we can write out this summation, and if you do that, you'll get the results that are shown here. And we can let D11 and D22 are by definition 0. That's the result from the previous page. And what you find, if you set these guys, D11 and D22 to 0, the result from this for a binary case is that D12 is equal to D21, and we often give these diffusion coefficients a special nomenclature. I'll start to use a star with them. These are the so-called binary diffusion coefficients. And so what this is saying is that in a two-component mixture, this expression tells us that there's only one independent diffusion coefficient that governs the diffusive mass transfer between two components in a mixture. And if you think about it a little bit, that has to be the case. Because if the J sub A's are to add up to B equals 0 in a binary system, then whenever I have the transport of A in one direction, I must have, that's equivalent to having an equal and opposite transport of B in the other direction. And so these binary diffusion coefficients must be equal to one another. Now, once you go beyond two components, that is to 3 or more components, these generalized diffusion coefficients are, DAB is not equal to dBA in general. This poses a problem in modeling mass transport phenomena in multi-component systems, in that there are many additional coefficients that enter the basic mass flux expressions, and you'll find that a lot of the work in the literature is based upon binary or pseudo-binary approximations for this reason. It's just that it's quite difficult to apply particularly to liquid systems and solid systems, to apply the multi-component generalized transport phenomena. But we show you a little bit about that just so you'll see what some of the issues are in this. And so if I expand that sum that gives the relationship between the diffusion coefficients for a case where we have 3 components, and I'm going to let B and C, I'm going to let component A be 1, and then I'll let B and C vary from throughout the sum as shown here. There's a number of these terms that are equal to 0, and I can write each of these relationships for various combinations of B and C being 1, 2, 3, etc. And if you do that, what you'll find that for a ternary system, there are 6 possible non-zero multi-component diffusion coefficients. If you work through the math and the algebra here, you'll find that the criteria that we've just shown here provide 3 independent equations that relate these 6 diffusion coefficients to one another. And so you need further information to fix all of the diffusion coefficients in a ternary system. And if you go to even more components, the situation becomes becomes more complex. So if you go to a 4-component system and go through the analysis we just looked at, there are 12 possible multi-component diffusion coefficients that are not equal to 0. And the criteria above provides 6 independent equations between them. And so that means that for a 4-component system, you have to make sufficient measurements to fit essentially 6 or determine essentially 6 multi-component diffusion coefficients. And so I'm going to show you a different approach here in a little while to this to modeling this phenomena. But in general, there's as you go to multi-component situations, you introduce a considerable amount of complexity in the solution of these problems if you solve them rigorously from first principles according to the models that we're developing here. Now, very generally, the diffusive mass flux is often broken up into several pieces that reflect the dominant driving force for a given phenomena driving mass transport. And so if I go back to the expression earlier, I can rewrite the diffusive mass transport in terms of a piece that depends upon concentration gradient driven diffusion, pressure driven diffusion, species-specific body force driven diffusion, and thermal diffusion. So all I'm going to do is rewrite the original expression for the diffusive mass flux. I'm going to break it out into these 4 components. And so the first one describes what I would call ordinary diffusion, or if you will, concentration gradient driven diffusion. You can see here that gradient is essentially given in terms of the gradient and chemical potential, but now expressed in terms of concentration gradients. The pressure diffusion term has the pressure term in it. The species-specific body force, or often called force diffusion, which is often important in ionic systems, that term looks like this. And the thermal diffusion term is given by this expression, equation 17, and that's often called the Sorey effect, named after one of the scientists who did a lot of work in the thermal diffusion area. And again, these are just breaking apart that initial expression on the first page of the notes into its various pieces. And we're going to first look a little bit at binary systems, because these are by far the most commonly used mass transfer expressions to solve practical problems. And so for binary systems, we start with the general expression for mass flux. And I've gone ahead and evaluated the sum here, assuming that DAA is equal to 0. In the binary systems, the generalized driving force of A is equal to minus that of B because of this relation that requires them to sum to 0. That's the relation that we'll ask you to prove in homework. The diffusive mass flux of A is equal to minus that of B. Again, this is a relationship we've seen previously. And it turns out that these thermal diffusion coefficients in a binary system have to be equal and opposite to one another. If you imagine a binary mixture of components, and you have them in a tube, and one end of that tube is heated, this will cause mass transfer due to thermal diffusion. And if the thermal diffusion coefficients are greater than 0, then species A moves from hot to a cold region. And if it moves from the hot to the cold region, then species B has to move in the opposite direction. And so its thermal diffusion coefficient has to be negative. In general, diffusion coefficients are positive for mass transfer. One of the only wide exceptions to that rule is in the case of thermal diffusion, where with thermal diffusion you always have at least one of the thermal diffusion coefficients in a multi-component mixture has to be negative in order to allow the species to respond differently, to move from hot to cold regions versus from cold to hot regions. We'll see examples of this a little bit later. Now, from this relationship, I've gone ahead and put the little star on the DAB here to recognize that we're in a binary system, so these will be binary diffusion coefficients. And as we showed previously, DAB is equal to dBA. That comes from this particular constraint on the diffusion coefficients. I can also write the mass flux of A not in terms of the generalized driving force for B, but in terms of the generalized driving force for A, since the sum of these generalized driving forces has to be 0. So dA can be replaced, or dB can be replaced with minus dA, and that's what I've done in this particular expression. And now if we expand out d sub A, we get the result that is shown in equation 24. If I further recognize that the mass fraction is the mass concentration of A divided by the total mass concentration, or the density, and that omega A, the mass fraction of A, is 1 minus the mass fraction of B, I can write that expression or simplify it a little bit as shown here. And in order to use this in practical solution to practical problems, we need to have a relationship that relates the chemical potential of A to composition, so that we can evaluate this expression in terms of temperature, pressure, and composition. We build models around it, thermodynamic models that allow us to input the effective chemical potential into the mass transfer, the changes in chemical potential with composition into the expression for flux. And so we need also to be able to express these concentration gradients not only on a mass basis but on a molar basis. And so we'll turn to these two tasks in the next little bit in the notes. And so the general definition of chemical potential, and I'm going to do it now on a mass basis, not a molar basis. The general definition of chemical potential is it is the change in the Gibbs free energy of a mixture with respect to a change in the mass of one component, temperature, pressure, and amount of all other components held constant. That's what all these little subscripts mean. And this is a little bit different from the chemical potential that you may have encountered in undergraduate thermodynamics, which is often defined on a molar basis, the change in the Gibbs free energy with respect to a change in the number of moles of component A. You can also write chemical potential on a mass basis, and so this is helpful in the case of the mass transfer. Results that I'm going to show you, and so I show you a little bit about how to work with chemical potential on a mass basis, and it's on a mass basis because the m sub A is the mass, not the number of moles of component A. Now, of course, the mass is simply related to the moles by the molecular weight, so this is not anything broadly different from defining chemical potential on a molar basis. I can, in general, define an activity, A sub A, in terms of that chemical potential, as shown in equation 26. So the activity is basically defined as the chemical potential relative to the chemical potential at its reference conditions. Often that's pure A or infinitely dilute solution of A in B, depending on the situation. But the activity is basically has the concentration dependence or the composition dependence of the chemical potential in it. And I can write these gradients in the chemical potential with respect to composition of d mu A d omega B, I can write that in terms of the concentration of the mass fraction of component A, because d omega B has to be equal to d omega A because the mass fractions sum to 1. And so I can write this term in terms of the change in the logarithm of the activity of A with respect to composition. I can then show the relate the this term to the form that is shown here, so that I basically bring this mass fraction term into the derivative with the activity. And then that first term for the generalized driving force takes on the following form. And now we see the flux of component A in this form being related to the gradient in mass fraction of component A. So this is beginning to look a little like Fick's law, where you have the flux is minus a term that we'll come to show is what we typically call the diffusion coefficient times the gradient in the mass fraction of component A. We can also have pressure induced diffusion and species-specific body force induced diffusion. Thermal diffusion is already in here. So this gives us a consistent way to include all of these effects into the diffusion flux expression. Now you can also, of course, define chemical potential and activity on a molar basis, and I'll use a little superscript N to denote the molar basis, whereas without the superscript, that's the mass-based chemical potential that we just walked through. And we define the molar-based activity in exactly the same way as we did earlier. And then the gradient in the chemical potential of component A can be written as shown here. And I would like to note that if we define an ideal solution as d log A with respect to d log xa equal to 1, this simply implies that the activity coefficient is independent of composition in an ideal solution. If we define the activity coefficient as the ratio of the activity to the mole fraction of A, and this is a very typical way to define activity coefficients in gas or liquid systems, or for small molecules in gas, liquid, or even solid systems. Now, in polymers, very often we use as the composition variable the volume fraction of component A, but that's a detail in this analysis and doesn't affect the general conclusions that we're drawing. And so, with this definition of the activity coefficient, I can write the change in the log of the activity with respect to the log of the mole fraction as shown here. And if the activity coefficient doesn't change with composition, this term is 0, and therefore we have a thermodynamically ideal solution. So to obtain these, the mass flux in terms of mole fraction and the activity based on a molar basis, we need to relate these mass fraction driven concentration gradients to mole fraction basis, and we do that by using the definition of mass fraction and the relation between mass fraction and mole fraction that is shown here. If you simplify this expression, the term on the bottom can be written as the molar concentration divided by the density in the solution. So this is the total moles of moles in the system divided by the total number of grams or the total mass of the system. And if you work out this summation, you'll see that connection. For a binary system, I can write this result as shown in equation 37. What we need for these derivatives is d omega A and d omega B, and so I can take the derivative of omega A, or the differential of omega A, and the result of that is shown here. I can rewrite it as shown in equation 38, and you should verify that the results follow as a result of this definition of the total mass concentration and the total molar concentration, or the mass density and the molar density. I can insert this result into or use it to develop the expression for the relationship between the mass-based concentration and molar-based concentration. I can then simplify those as shown here and put them back into the original expression that we're working with in terms of mass fraction gradients for concentration. And if I do that, I get the result that's shown in the red box at equation 44. And if I further relate the now I have the mass flux written in terms of gradients in the composition of A on a molar basis. I can also write that in terms of the mass fraction basis. And if you do that, you'll have in the expression, the box expression in equation 46, which is that the mass-based flux is equal to minus rho times this binary diffusion coefficient times the thermodynamic term times the gradient in the mass fraction of component A. Very often we would write the term in brackets as I call it DAB0, and that's the so-called effective binary diffusion coefficient. And now this looks exactly like Fick's law. The mass flux is equal to minus the density times the diffusion coefficient times the gradient in mass fraction of A. If the density is not changing in the system, I can bring rho inside this grad omega A, and I would have then that the mass flux is equal to minus the diffusion coefficient times the gradient in the concentration of A, which is what you would recognize as Fick's first law. And it points out that the diffusion coefficient in Fick's first law contains both a kinetic piece as well as a thermodynamic piece, this d log A, d log xa. So the thermodynamics of the system can influence the diffusion coefficients. Very often in practical situations, we lump these two effects together as shown in these brackets to get an effective overall diffusion coefficient. What I'm mainly trying to show here is that the expression that we know and have used, that is Fick's first law, follows from this more generalized machinery for including effects of driving forces other than simply concentration difference. Also trying to make you aware of the fact that these diffusion coefficients do have a thermodynamic contribution to them, the diffusion coefficients as we normally use them. Now, I can also write the mass flux in terms of gradient and mole fraction. I get again an effective diffusion coefficient. I give it a superscript R, but it is essentially again a term that we often lump all of these terms together when we're measuring diffusion coefficients and reporting them in real systems. And so the final form of the expression for the diffusive mass flux for component A is shown in the red boxed expression at equation 58. And it includes effects from thermal diffusion, it includes effects from concentration gradient driven diffusion, pressure driven diffusion, and also species specific body forces. Now, I want to share with you another variation or another approach to this issue of multi-component transport that's often widely used. And it's the so-called Maxwell-Stefan equations, and it proceeds from the following point of view. What we have done so far is we've written the diffusive mass flux, that is these J sub A's, in terms of gradients in composition of A, gradients in pressure, gradients in temperature, and so forth. That is, the flux is written in terms of the gradients that drive the transport. It turns out that there are certain classes of multi-component problems where it is advantageous to write not the fluxes in terms of the driving forces, but to write the driving forces in terms of the flux. That is, to invert this expression, and that generates what's known as the Maxwell-Stefan equation. And so I'm just going to show you this briefly. We'll use it a little bit in multi-component transport as we move along. But basically, you can imagine writing out these this sum for all of the n components in a mixture, and then writing one such equation for each of the n components in a mixture, and you would have basically a matrix of equations relating the fluxes to the generalized driving forces. And you can invert that matrix to get a relationship between the driving forces and the flux. And Hirschfelder, Curtis, and Bird have done this. And when you do so, you get an expression relating the generalized driving force to a term that basically includes these J sub A's, now written in terms of the velocities of the components, VB and VA, and a term that also includes gradients in temperature for thermally driven diffusion. This first term is the one that is often seen in the Maxwell-Stefan, when you see the Maxwell-Stefan relations written out. And so if we write the mass flux as the molar concentration times the average velocity of component A, we can get the expressions that are shown here, and we can combine this expression with equation 54 to get the generalized driving forces in terms of the fluxes in the system. So previously, I'm writing the flux and the diffusion flux in terms of the gradients that drive the diffusion. Here, I'm writing the gradients in terms of the total flux of the components in the system. And this is called the so-called generalized Maxwell-Stefan relation. And if we go ahead and further write the generalized driving force as shown here in equation 56, you can imagine putting this on the left-hand side of equation 55 to get the most generalized form of the Maxwell-Stefan equations. Somewhat more useful forms can be obtained by recognizing that this sum, and if you write this out, it's a little bit easier to see, this sum can be written as only this single term. And so if you write this out, you can see that this is the case. And if this is the case, then I can write the generalized driving force for the Maxwell-Stefan equation as shown here. And the popular form, or the most often seen form of the Maxwell-Stefan equations, is not the one with the generalized driving force, but it's a somewhat more idealized form. And so if we assume ideal solution, then this activity term is equal to 1. If there are no pressure effects, then this term involving the pressure gradient is 0. And if there are no species-specific body forces, then this term involving the F sub A and F sub C are 0. Further, if there are no thermal diffusion effects, we can get from the generalized result, we get the result that is shown in equation 59, and this is what is classically known as the Maxwell-Stefan equation. It relates the gradient in the mole fraction of component A to the molar fluxes of A and B in a multi-component system. You can write one of these equations for each of the components in a system. Of course, only n-1 of them are independent, because if you sum up n-1 of these mole fractions, then you get the final mole fraction. So anyway, these are the Stefan-Maxwell equations, and it turns out that this is a useful approach to modeling mass transfer in multi-component systems, and I'll show you how to do that a little bit later. Now that's the end of our discussion of the multi-component system. One of the things that is very typically done in practical problems is to use the so-called effective binary diffusion coefficients. And that is to reduce multi-component problems to problems that involve essentially effective binary that are modeled using a binary, an effective binary model. So what does that mean? Well, if we consider our diffusion coefficient as it's defined in a binary system, you'll remember that we wrote our constitutive equation as minus the molar concentration, binary diffusion coefficient. It's often called the mutual diffusion coefficient because it's the diffusion of A in B, so it's the commingling of two mutual components, times the gradient composition plus the convection correction term. I can write these terms alternatively in terms of the molar diffusive flux and in terms of Ca times the molar average velocity in the system. This result, I will assert to you, and you can now prove, assumes that we have an ideal solution. There's no thermal diffusion, no pressure diffusion, no species-specific body forces. And so in many multi-component systems, it's often useful to define, by analogy, a binary diffusion coefficient of species A in that multi-component system. For example, if you are interested in modeling the dispersion of a pollutant, say an organic chemical, in air, very often the way this will be modeled is not to treat air as a 1,000 component system with your pollutant, oxygen, nitrogen, CO2, argon, and go on down the list of all of the trace components that may be in air. But it's to treat that mixture as a pseudo-binary mixture where the component of interest is diffusing in a mixture and its diffusion coefficient is given by an effective or average diffusion coefficient. And so what we will do is we'll take this definition of mass flux, or if you will, the binary diffusion coefficients in a binary system, and we will write an effective form of it in a multi-component system. So we imagine now that we have not the flux of A in B, but the flux of A in a mixture of many components, potentially. Now this expression reduces to the one above in the case where there's only two components, but in principle one could have many components. And we will use this as the defining expression for these effective diffusion coefficients, effective binary diffusion coefficients. And so if I equate these two, or if I take this term and write it in terms of the gradient in the concentration of A, and then compare it with the Stefan-Maxwell equation, which was derived rigorously for multi-component mixtures, I can combine these two results and I get an expression that relates the multi-component diffusion coefficients, that is the diffusion of A in the mixture with the diffusion coefficients of A in each of the binary components of that mixture. And so we will use this to develop expressions for these effective binary diffusion coefficients in multi-component mixtures for a number of simplified cases. And so we will also assume that we're very often working in situations where we're dilute in one component that we're interested in knowing its transport properties, and so we'll assume that the mass and molar average velocity are the same. That can be relaxed, but that makes the following discussion somewhat simpler. The average molecular weight of the mixture is rigorously given by the mole fraction of each component times the molecular weight of those components. And if you have a situation where you have a dilute solution where a component of interest, that is component 1, is diffusing in a where a component is diffusing in essentially pure background material, which we'll call component 1. And then this average molecular weight can just be given by the molecular weight of the component that is there in large concentration. And this provides the following relationship between the mass average concentration and the molar average concentration in the mixture. So let's look at just a few limiting cases. One is where you have trace components diffusing in nearly pure 1. And I'll call 1 as the dominant component in the system, and you have trace components 2, 3, 4, etc., diffusing in nearly pure 1. So think about a situation where you have, for example, a liquid like water, and you bring that water in contact with air, and some of the air gases dissolve into the water. So you have a little bit of oxygen, a little bit of nitrogen, a little bit of carbon dioxide, and so forth and so on, dissolved into the water and diffusing in the water. But the water in that case is by far the dominant species, and so it's the nearly pure 1 in this case. And what we'll show is that the diffusion coefficient of any of these trace components is equal to the diffusion coefficient of that component in pure 1. So considering the case of air that's that's in contact with water, what this is saying is that the diffusion coefficient of oxygen in that aqueous mixture that has water, oxygen, nitrogen, and all of the air gases dissolved in it, that the diffusion coefficient of oxygen in that mixture is equal to the diffusion coefficient of oxygen in water, absent all of the other trace components. And you can imagine this is a powerful result because it allows you to make a binary measurement, for example, the diffusion of oxygen in water, and then use it in cases where you have many components, as long as they are present in trace amounts. And you can imagine, I hope that what it's telling you is that if these other components are present in trace levels, then they don't much affect the diffusion of each other. They don't see each other, and so they each diffuse essentially independently of one another. And that's a very powerful simplifying assumption. It allows you to reduce, potentially very complex multi-component transport problems to binary problems. And this is why we study the solutions to the binary transport so much, is because many of the multi-component problems are mapped onto effective binary equivalents or analogs. And you can prove this using the result that we derived earlier. For example, if you consider the diffusion of component 2, that could be nitrogen, for example, or oxygen in this mixture, and you basically work through the mathematics. When you have x2, x3, and so forth going to 0, and only x1 being nearly equal to 1, then this is the only term that survives out of the numerator, and you can write that expression in the following simplified form and derive the result that we showed you in the box just a minute ago, and that is the diffusion coefficient of one of those trace components in the mixture is just equal to the diffusion coefficient of that trace component into the background material, the water, if you will, in the case we were using, absent all the other components. So you can use binary diffusion coefficients to track or monitor the diffusion of each of the species of interest independently of one another. And so if you have a situation where all of the diffusion coefficients are equal, then you can show that the diffusion coefficient of A in the mixture is equal to the diffusion coefficient of A and B. So this is helpful in, for example, gas phase diffusion, where often the diffusion coefficients of many components are of the order of 0.1 square centimeters per second, so they often have very similar diffusion coefficients, and so this helps simplify the diffusion coefficients in mixtures. And so the proof of this relationship proceeds very similarly to the one we just did, and if you let all of the diffusion coefficients DAB equal 0, they come out of the sum, and if you evaluate this term in brackets, it's just unity or -1, and so the results simplify as indicated. Another case of interest is where you have a solution where species 2 through n either move with the same velocity or they're stationary, and only one component is effectively on the time scale of interest. Only one component is effectively moving or diffusing, and you can derive the relationship shown here between the diffusion coefficient of that species that's moving in the mixture and the diffusion coefficients of that species with each of the other components that are in that mixture. And I won't belabor the definition here or the derivation just to get to the bottom line. And this result is often useful, for example, to calculate the mass transport of a species of interest, for example, a pollutant diffusing through stagnant air. It's basically the diffusion coefficient of that component of interest, the pollutant in the mixture of air, can be estimated from the binary diffusion coefficients of that pollutant in the oxygen, nitrogen, etc. In air. And so you can estimate the mixture diffusion coefficient based upon the diffusion coefficient of that component through binary combinations with the other species that are in the mixture. And so that is the basis behind the so-called effective binary diffusion coefficients, and why you'll see us solving problems that are inherently multi-component, like the transport of a component of interest through air, or even the transport, for example, of oxygen in water. You can imagine that water, as you get it out of the tap or in any natural situations, it has a lot more components in it than just H2O. It may have some salt in it. It may have other dissolved gases. But we can model the transport of a component of interest through that medium using these effective binary diffusion coefficients. And if we're in one of these limits, which is often the case, then the modeling is on a very sound theoretical basis. And so this is why you see it so widely used that way, this binary approximation, even in situations where very typically it's not just a binary system. So here are some widely used approximations for mass transport in binary systems. One is the assumption of zero velocity. We'll start first with our species continuity equation in mass and molar units. And you often have this assumption where you have one component, a trace that's present in trace amounts, diffusing through a solid or a liquid that's not moving. That makes the average velocity equal to 0. And in that assumption, the total mass flux or molar flux is equal to the diffusive flux. So essentially, this is the case where you have no convection. And with this simplification, the mass balance can be written as shown here in mass units, or over here in equation 4 in molar units. And at constant temperature and pressure, and in the absence of species-specific body force and chemical reaction, we can write these fluxes as shown here and write the continuity equation of the species-specific mass balance as shown in equation 7. The molar analog is here. If the molar concentration or mass concentration in the case of mass units is constant and the diffusion coefficients are approximately constant, we can bring those terms, bring the C into the derivative, bring the DAB out of the derivative, and you get the form of Fick's second law that we typically know. You can write that either on a constant mass concentration basis or on a mass fraction basis, mole fraction or molar concentration basis. And so this is the most widely used form of Fick's law for transient mass balances where there's no convection and no chemical reaction. There are books written on the solution of this differential equation A very famous one is called The Mathematics of Diffusion by John Crank, and it is hundreds of pages full of analytical solutions to these diffusion equations. They're so important in the physical sciences. There is an analogous book called Conduction of Heat in Solids that solves the analogous problems in heat transfer, and it is again very widely used in heat transfer. Very often we have a situation where we have a constant mixture molar concentration. That is, where even though mass transfer is going on, the total molar concentration is not changing. And so, with this approximation, we can write the species continuity equation as shown here. We should verify that. And if we also use this result, the previous result for Fick's law, we obtain the continuity equation as written in equation 11. This is often the so-called convection diffusion equation. So you'll find